Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we did talk about a parallel circuit. We said in parallel circuit, of course, if we had, of course, let's say a coil, a resistor and a capacitor, let's say all connected together, but in parallel circuit. We said in parallel circuit, the voltage were the same, let's say across each one of the loops. And then, of course, we used to combine, let's say, I total, or in another way, we used to find the current through the resistor, the current through the coil, and the current, let's say, or IC as well, we can say. And of course, we used to add them all together. And of course, we said I total or I effective total equals to the square root of IR plus. But remember, IC this time minus IL, and then close bracket, then square the whole bracket, let's say. And of course, that was for the current. And then, of course, we said we can find the resistance as well. For the impedance, it was 1 over, let's say, fraction, the square root of, let's say, 1 over r squared, let's say, we can say, of course. And then after that, plus, let's say omega c minus 1 over, it's hard to, it's a bit hard to imagine all this, but of course you can, if you know, you know it, yeah? Okay, so minus 1 over omega L, and then close bracket, and then square this. So this is basically how we used to find the total impedance of the circuit. And then, of course, we said in order to find the phase angle difference between the current and the voltage, of course, we used to say tan theta was equal to IC minus IL over IR. That was one of the ways to find the angle difference, or let's say by what degree would it be the current leading or lagging behind the voltage. So we've covered all that, and then we stopped right at this point here, the oscillating circuit. What do we mean by oscillating circuit? And of course, we did talk about this one, by the way, as well. In parallel circuit, we said that this parallel circuit can also be an oscillating circuit if omega c was equal to, let's say, 1 over omega L. And of course, in that case, let's say R was equal to Z. We said the resistance would be maximum in this case. And of course, we can say that the current will be minimum in that case. But it is different when we have in series circuit, yeah? So that is basically what we have for an oscillating circuit. So you can see the oscillating circuit is made up of a self and a capacitor connected as in these, you can say as in this figure, as you can see here. So take a look. This is a capacitor. Or by the way, this is a variable capacitor, you can say. Okay, so that means we can increase or we can change the value for the capacitor here. But remember, capacitor is initially charged with, or you can say under an external DC source. So once again, remember, this capacitor cannot be charged with an alternating current. Why? Because the polarity of the current changes, let's say, every half a cycle. If it is alternating current, so maybe let's say one side will be positive for half a cycle, the other half a cycle, the other side is going to be positive. So we end up with 0 negative or 0 net charge on the two plates, let's say. But if it is a DC, one side, let's assume that is going to be positive, the other side is going to be negative. And of course, this is how we can, let's say, charge the capacitor. So, but don't forget, right, we will have to use an external DC direct current so that we can charge the capacitor. Then the circuit will oscillate at a frequency that depends on the values of both the capacitance and, of course, you can say of C and L, that would be the coil, you can say. Okay, so how does the process of oscillation works here? Okay, so here's the thing. If the initial charge on the capacitor is Q naught, we can say after the capacitor has been charged with an external, let's say, DC source, then of course we have, let's say, some charges over the capacitor. The amount of charge, we can say it is equal to Q naught, okay, that is the charge that we have. But remember this, then the electrical energy on a capacitor, we can say the charge will be stored as electrical field here. So now we have stored some charges on this, and of course, so this energy that is stored on the capacitor will be in the form of electrical energy. But then what happens? Remember this, up to this point, we have only stored some electrical or some charges on the two plates. So these charges are not oscillating, not flowing through the circuit. So if it is not flowing through the circuit, you can see that the current in the circuit at this point is still 0 because there's no current flowing. Then the capacitor discharges through the coil while the current increases to achieve maximum, let's say, volume. So of course, now you can see here, this side is positive, and of course the other side is negative. Let's say that the charges are going to, using, let's say this is the direction of the current, even though electrons will move in the opposite direction, you can say. So the charges start to move through the circuit, all right? And of course, once the charges start to flowing, this charge, where the flow of charge increases more and more and more, let's say, until it gets to maximum value. When the capacitor loses all its charges, we can say that is the point when we have maximum current passing through the circuit here. But then what will happen to this electrical energy that was stored onto the two plates of the capacitor? The energy is now, it is stored in the coil, but this energy, after it is stored in the coil, of course, it is going to be in the form of what? In the form of a magnetic field, let's say. Okay, so let's just assume that this side is positive north and the other side is south. You can see that that's basically what happens. And now this energy is stored, let's say, on the coil, you can say. As what? As magnetic field here. But then what do you think will happen later on? Now this magnetic field, of course, once again, it is going to be converted to, you can say, electrical energy or electrical current, and then of course it bounces, or you can say goes back. It will be stored on the capacitor plates again, but there is one difference here. So if the first time this side of the plate were positive, after, for example, this have went to the electrical energy, have went to onto the coil, and then now this time the other side is going to be positive, this side is going to be negative, or you can say the polarity of the two, let's say the charge on the two plates will be different, of course, so that to make sure that these oscillating continue back and forth between the capacitor and between the coil as well. So this charge is again restored by the capacitor until the current in the coil drops to zero. So like we said, now after the current is stored here, then the current start to let's say flow through the circuit as well until we have maximum current. That is when no charge, or let's say no energy, is left on the coil there. And of course, the energy is again stored on the capacitor and so on. So this process continues, let's say, back and forth, back and forth. The energy will be stored on the capacitor, then after that on the coil, let's say again on the capacitor, on the coil, so it goes back and forth. So if no energy is lost, this process will continue, you can say. Okay, so the exchange of energy is repeated many times between the capacitor and the coil, as long as no part is lost through the resistance of the coil as a form of heat, you can say, okay, or in a form of heat. Any possible loss leads to a damping. So this oscillation between 1 and 2, of course, if there's energy loss, you can see that this energy will decrease more and more and more until, let's say, the frequency between these two becomes lower and lower. And of course, that is what we mean by damping. So the energy is lost. So this energy that is stored will be lower every half a cycle, you can say, or every cycle. And then until we end up with no energy at all. Okay, or you can say no oscillation at all at that time. So any possible, we've went through this one. Point 8 says, if a current of the same frequency and phase difference, you can say, is introduced to the circuit. So you can connect, let's say, one of these circuits, let's just say, to a current that has the same phase difference, let's say, and of course, frequency, right, introduced to the circuit, then of course resonance will happen. So of course you can see that there is an oscillation here. If we, let's say, connect a circuit, or let's say a source of the same frequency, let's say in phase difference, you can say, then in this case, this too will be oscillating, of course, or you can say the whole circuit will be in a state of resonance, or simply resonance will take place. So as you can see, this is basically what happens, or you can see what happens, for example, when the charge is stored on the capacitor, and then after that, the charge will be stored on the coil as a magnetic field, and of course, vice versa, you can say. But there are a few things you need to know. The circuit enters into resonance when a current of, let's say, given frequency is injected to it. So this current, or this source that you add to the circuit, of course, it has a certain frequency. If the frequency of the source matches the frequency of this circuit, then of course this too will be in state of resonance. While the capacitors and the capacitor, by the way, sometimes not all these are equal, yeah? Let's just say the frequency of the source that is, let's say, injured or connected with this one is not the same. So we talked about this variable resistor, yeah? So we can adjust, variable capacitor here. So we can adjust, increase or decrease the value for this capacitance so that we can say that the frequency of this circuit will match the frequency of the external circuit, so that this two circuit will be in a state of resonance. And when that happens, of course, we can say this is how one, let's say, can tune the frequencies of a radio and television stations at home, and of course the resonance takes place. The reception, of course, of the broadcasting station is possible. So you're sitting inside the car, let's say, you're just tuning your radio, and just to say, for example, and then once you're tuning in, let's say, of course, you will be receiving, let's say, I don't know, one of the radio stations broadcast, let's say. Now you can hear them, you can listen to their, let's say, to their broadcast, whatever podcast, whatever they are, let's say, whatever they're broadcasting here. And the reason why, because once you're adjusting or tuning this in, of course, that means you're adjusting the frequency of the radio or the circuit that is inside this radio to the frequency of the external source. Let's say once these two, of course, match, then the circuit will be in a state of resonance. Then, of course, you can receive, let's say, the broadcast. Okay, and of course, you can hear the radio, whether if it is a program, could be whatever they're broadcasting you. So there are two study tips I want you to know here. The first one says a capacitor charges with the DC voltage only. Don't forget, okay? And that is, of course, storing energy as a potential difference between the two plates. With AC, like what happens if you use an AC? And of course, it continuously discharges and charges. So this continuous charge and discharge, of course, you get a net, let's say, zero charge on the two plates without maintaining a steady charge on the two plates here. Now, there are a few things that are very important regarding the resonating circuit, or when we have a circuit that is in a state of resonance. The first thing here, you need to know that in a resonating circuit, XC is equal to XL. That is one of the most or first thing you need to remember. And then another thing that we have, if these two are equal, we can say the entire resistance of the circuit will be equal to the resistance, let's say, of the pure resistance only. So we will consider the resistance of the circuit to be just equal to the R, or the resistance of the resistor here. So we will not consider the resistance of these two, because these two will be equal. You can say, so of course we'll get, so the entire impedance or the entire resistance of the circuit will be the resistance of the resistor here. And if that is the case, of course, if these two are equal, we can say the voltage across the self-inductance here, it is the same as the voltage across the capacitor. And if that is true, okay, of course, for this one here, so that is basically these two are related, you can say. This two, and of course this one as well. If we consider, for example, we said the total impedance is equal to the resistance of the resistor, so we can say V total is equal to the voltage across the resistor as well. See, so these are some of the properties, by the way, of a resonating circuit. So you can consider this to be point number one. And another point is that, remember, the resistance is minimum. And if the resistance is minimum, what do you think about the current? Resistance and current are inversely proportional. So if resistance is minimum, the current through the circuit or in the circuit will be maximum. And of course, you can say, so basically the current is maximum. That is the third point. The fourth point is the phase difference is always zero. So you might be, or a lot of times, especially in Wazari, national exam questions, they would tell you, for example, what is the phase difference? Or sometimes they might tell you a resistor, a self-inductor, let's say a coil, and also a capacitance. These are all connected in a circuit, but the circuit is in a state of resonance. So what is the phase difference between, let's say, XL and XC? What is the phase difference, let's say, between XL and XR, whatever? So whenever you see the circuit is in a state of resonance, immediately go for the zero, because the phase difference in the circuit, it is going to be zero in this case here. Okay, because we said the entire impedance of the circuit is going to be R, and we said for a pure resistor, both the voltage and the current will be having the same phase difference here. Or no phase difference between the two, or just zero phase difference. And also remember this, we said that XL, or XC, you can say it is equal to XC, yeah? But what does XL is equal to? Equal to omega L, and of course this one is equal to omega 1 over omega C. Let me not, okay, so XL, omega L equals to 1 over omega C here. So, but, okay, if I take omega, or both omegas here, so of course I'll get omega squared equals to 1 over L over 1 over L times C here. But you do know that this omega equals to what? Omega equals to 2 pi f, correct? And don't forget it is squared. So in this case, of course, I'll have 4 pi squared f squared equals to 1 over L C here. So remember, this is f squared here. So if we want to find the frequency, okay, that the circuit is resonating with, we can say frequency equal to, well, let's just take the frequency squared for now. Okay, equals to what? Equals to, we can say 4 pi squared times L times C. That is, of course, 1 over this. But we want frequency, not frequency squared. So you can take the square root for both sides. So we can say frequency, these are in the square root, equals to 2 pi, comes out, and of course becomes the square root of L times C. So this frequency is, we can say, this is the frequency that the circuit is resonating with or the resonance frequency of the circuit as well. But you don't have to go through this one all the time. Whenever they're asking you for the frequency of the resonating circuit, you can just say frequency equal to 1 over 2 pi, of course, the square root of L times C here. Okay, so this will be the equation again. That would be for this. And of course, for example, if we have a question here, says what? For example, if C is 0.25 microfarad and L is 5 millihenry, the resonance frequency will be what? So you have the equation, just write the equation, plug in these values into the equation, and then of course you could just simply, that is basically for L, okay, so this is this value, that is milli, 10 to the power negative 3, and this is for the value for the capacitance micro, that is 10 to the power negative 6, so you can say, so this is the frequency that the circuit is resonating with. Okay, now what does the frequency of a resonating circuit depends on? As you can see from this equation right here, the frequency, these are all constant, yeah? So it depends on L and C, but you can say it is inversely proportional with, just not with the L, you have to be careful here. You can say it is inversely proportional with the, let's say, radical, okay, or let's say L under the square root of, or under the square root, you can see here, and of course with the value of C as well. So to simplify this, we can just say it depends on the value of L, that is basically inversely proportional, you can say with the square root of this one, okay? And of course it is inversely proportional with the square root of C as well. So this is what the frequency of a resonating circuit depends on. And now we have few exotic questions. These are also very important. The first one says, tuning the frequency of a radio and television station at home to make a good reception of the broadcasting station is one of the applications of what? That is, of course, one of the applications of electrical resonance. Which of the following represents the electrical resonance equation? And of course that is, you can say B as well. Now take a look at this one. This is something very important. For an AC series resonance circuit here, if these are what we have like the components of the circuit, R, L, C, which of the following is correct? We said, remember this, one of the most important property of this, XL and XC are equal. Here says bigger, smaller, equal, that is the correct one. Here says this is bigger than V total, that is incorrect. So the correct option is going to be C. Okay, for an alternating series resonance circuit, these are, you can see which one is incorrect here. This is correct, this is correct, this is also correct, so this is incorrect because we said for a resonating circuit, the total resistance of the circuit will be the same as the resistance of the resistor here, so this is incorrect. All right, this is one of the questions that I was mentioning earlier. It says what? An alternating series resonance circuit made up of a resonant, let's say made up of a source resistor of a pure resistance, an inductive coil, and a capacitor. The phase difference between the total potential difference and the current. You see, because we have resonance, you immediately go for 0 degrees between the total current and the potential difference, you can say. Phase difference between the potential and the current, or total potential in the current, is going to be 0. We charge a capacitor, remember this. So we said we charge a capacitor under AC voltage source or DC voltage source. We said it has to be DC only, otherwise it would be incorrect. Okay, and for this one here says an AC source is connected across a series of combinations of inductive coil with a specified resistance and inductive impedance of this much, and a capacitive with a capacitance, let's say capacitance with a capacity of this much, reach to resonance. Find the resonance frequency. How do you find the resonance frequency? You have these two together. So you have, it says, but the inductive coil, resistance of inductive impedance, that is basically 65 ohms. And of course you have, let's say 49 microfarad. So reach to the resonance. So at resonance, find the resonance frequency here. So how would you find this one? Remember this? I want you to be careful with this one right here. We said that, okay, finding the resonating frequency here, of course, we said that this two, basically XC equal to XL in here. But remember, XL is given to you because it says an inductive coil with specified resistance and inductive impedance here. So the XL is given, which is 65 here. So let me get this one in a triangle or a square, whatever, so we can solve this one, because I think this worth solving this together. Okay, so take a look here. We said, let me go this way. XL is equal to, let's say XC, but XL is given, which is 65, yes? And of course, XC here, that is basically 1 over, we can say, can I say 1 over omega C? Yes, and of course, 65 again, 1 over omega C basically. Omega is 2 pi f, yeah? All right, and then multiply by C. What we're trying to find is this frequency here. So can I swap their places? The answer is yes. So frequency is equal to 1 over, we can say 65 multiplied by 2 pi multiplied by the value for the capacitance, which is 49 micro, that is 10 to the power negative 6. You do the math, of course, you will find the answer. And I believe it is, I think it was 50. You do the math, and of course, you'll find the answer, which one it is, yeah? Okay. Okay, 7, that was B, so of course it was 50. Okay, what about the this question right here? It says what? An AC series circuit made of all this, an inductive coil and all that, okay? So we have a capacitive impedance equal to this. The frequency of the circuit is this much, is known as this in the circuit. What is the approximate value of the self-inductance of the coil here? So basically, you're trying to find L here. So now you have basically... okay, so basically it says what? What is the approximate value for the self-inductance of the coil here? So take a look. What you need to have is you have the frequency, correct? If you have the frequency, that means this is 2 pi f. You have the frequency, 2 pi f. You have the frequency, you have the value for the capacitance, capacitive impedance, my bad. So you have XC here. How about we solve this one as well? Okay, so now first of all, okay, let's say XC, that is basically 1 over omega C, correct? So now we don't have this, okay, we're trying to find this one here. So C, the value for the capacitance here is basically equal to 1 over omega, that is XC here. That is in another way 1 over 2 pi f times C here. My bad, XC. Okay, XC here. So the frequency that you need is given, which is 100, all right, write the frequency. XC, that is the capacitive impedance, which is also given. Using this, you can find the value for the capacitive or the capacitance of the capacitor. Once you do this, now all you need to plug it into the equation. Now you have this, all right, you have this, of course, you can find the approximate value of the self-inductance, you can say, and of course is going to be one of these. Now this is also something very important. It says what? The circuit, if the circuit is in the adjacent figure resonates, remember this, whenever it says resonates, try to underline or put it in a circle. Whether it is feeding current, what is the effective value of the alternating current here? So remember this, you have the V total effective, okay? And we said in resonance, the total impedance, or let me just go through this one here. V effective total equals to I effective, let's say, and of course, let's say the Z total, that is the impedance of the circuit. But don't forget, we said in resonating circuit, Z and R are equal. So now I can rewrite this one and I can say I effective R, correct? So I need this one here. So I effective equals to V effective total over R. And of course, you plug in the numbers, you'll find the answer. That is going to be 220 over this much here. That is going to be about 10, I guess. And of course, that is going to be C here. Okay, so this is how you can solve any question related to this. Now take a look at this one. This is also very easy. I'm not going to do this one because it is the same as the previous one that I've just solved here. Basically what you're trying to find is, says in a resonating circuit, basically the effective value of the alternating current. You just find the current. Don't forget you have the, let's say the total potential difference, or you can say the effective total. All right, so that was for that question. All right, now as for question 42, take a look here. This is also very interesting here. What does it say? It says a resonance circuit is made up of inductive coil and of course a variable capacitor. If the capacitance of the capacitor is lowered from, so we have two values, because it is variable, you can adjust it, you can increase or decrease. So here at this point we're going to change it from 400 microfarad to 100 microfarad. So the question is, what happens to the frequency of the circuit here? Now this is also interesting. So let's take a look and see what will happen to the frequency of the circuit if we change the value for the capacitor. Okay, so we'll keep this one here. So take a look. Now the equation that we have is basically, okay, for resonating circuit, yeah? Remember this, for resonating circuit, I'll write it here. We normally say F equals to what? 2 pi over the square root, let's say L times C. That is what the equation that we have. But because we're changing the value for the capacitor, so we can say we will have two frequencies, okay? So let's say this is, we'll say F2 over F1, yeah? Because we're trying to find what will happen to the frequency. Now, of course, I can rewrite this one in one step, but I'll show you something else before we write the main equation or the final equation for this one. Now, for F2 here, of course, the equation will be 1 over 2 pi, the square root of, let's say, L2. By the way, since the value of L is the same, so I don't have to say L2. And this, of course, we can say C2 here, and then divided by 1 over, okay, the square root of 2 pi, or before 2 pi, actually. So here's 2 pi, the square root of L times, we can say C1, yeah? Because that is for the first frequency, this for the second frequency, we can say. And of course, you can see that these will cancel out, correct? And then we can take the reciprocal of this one here. So what happens, this one goes to the top, this one comes under, you can say, this one comes here, this one goes to the top if we take the reciprocal. So we will be left with this F2 over F1, you can say it is, and of course we can write this two like together, we can say LC1 over LC, by the way, even the inductance will also cancel out here, so we don't have to write L in this case. So we can say C, that is 1 goes to the top over C2, these are square rooted. But of course, now we're going to use one square root for both of them now, yeah? So of course, we're going to say C1 over C2 here. Now, but remember this, okay? So we can say F2 over F1, you following? I hope, very, very good. So one of the values that we have, basically, we're changing from 400 to 100, yeah? So obviously, 400 is here. This is micro, yeah? So I'll keep it as micro here as well, and this is 100 microfarad. You can see these are cancel out, these two cancel out, this all that, yeah? So of course now we can say, this is the square root of an all that, yeah? So now we can say, lowered from this much, I think I've done the incorrect one here. Let me go back to this. Okay. All right, so remember this, we'll say C1 because we take the reciprocal over C2, yeah? If that is the case, we'll say F2 over F1, that is basically equal to C1, it is 400 microfarad, yeah? And then we're lowering this one to 100 microfarad. So these two will cancel out, and of course these two zero, this one and this. So of course we have the square root of 4 over 1. So the square root of 4 over 1, you do know that, we can say now F2 over F1 equals to the square root of 4, that is obviously 2, yeah? So it is going to be 2 over 1. Okay, now if we cross multiply here, we will see that F2, it is equal to 2 times F1, okay? This is what happens. But remember this, if they want you to know, for example, if they ever ask you what happens to the, let's say, frequency, or it will be the frequency, let's say, of, or F1 in this case, of course, you will take the 2 to the other side here. In this case, F1 becomes what? Becomes 1 over 2 times F2 in this case here. So it depends whether they ask you for this or not. Maybe they'll just tell you what happens to the frequency. So F2 is equal to, let's say, 2 times F1. This is pretty enough, pretty much. Okay, but if they want you to find, or what will happen to F1, that is going to be half of F2 in this case. Okay, that depends on the question, by the way, yeah? Okay, now take a look at this one. This is something also interesting. And I would really recommend you solving this one as well. And of course, this question as well. You can see that these values are lowered, so you're going to use something perhaps exactly the same as what we went through here. Now, okay, we have another question here. It says, and we have a, or you can say a circuit, basically, that has resistance, inductance, let's say, and a capacitance. These are all connected in series, made of a coil of self-inductance that is 15 millihenry, you can see. That is basically what we have. This is 15 millihenry. And of course, it says a resistance. This is the resistance of the coil, which is 10 ohms, don't forget. Okay, and then we have a capacitance that is connected, which is 200 micro. We can say 200 times 10 to the power negative 6 right away. Okay, that is in farad. And then resistor, and of course, a resistor of resistance 12 ohm as well. Okay, that is basically R for the pure resistance. This is R for the coil, don't forget, okay? And this is L. The value for L was 15 milli times 10 to the power negative 3 Henry. Okay, so if the effective value of the source, as you can see here, the source has, we can say V effective, that is 100 volts, and of course the frequency of the frequency of the source is 60 hertz here. Okay, now since you have all these information, you pretty much have an idea how to solve any question that they ask you. So the effective value for the potential difference across each of the coil, the capacitor, and the resistance. So how do you find the effective value of the potential difference across each one of these? So basically find VR, VC, and of course, not just VR and VL again, you will have to find the voltage across these two together at, let's say, as if it was one, or you could just say V of the coil. So I think we've solved questions like this or not, but I mean, perhaps yes. I'll give you an idea. Perhaps maybe I'll leave the rest for you guys to complete this one here. But let me just give you an idea how you can solve these questions. Okay, that is part of it. Okay, so moving this a bit. Okay, so this is what we have. Normally, how do you find, we have the V of the circuit, yeah? In order to be able to find the voltage across each one of these components, you need the current. But how do you find the current? We do know that V effective equals to what? I effective, that is the Z total of the circuit, yeah? In order to find the, let's say the voltage across each component, of course, we need this. Let's say if I want to find VR, I'll say I times R, yeah? If I want to find VL, I'll say I times XL, yeah? If I want to, by the way, for this one is a bit different here. We'll get into this in a second. For VC, we'll say IXC, yeah? Okay, but for VL here, it's a bit different here, guys, okay? Because we have the resistance, let's say VR for the coil, don't forget, okay? For the coil. So of course we have I times R for the coil, okay? Don't forget. And then for VL, that equals to I times XL. But then if we want to find V for the entire coil, remember there's a 90 degree between the two, of course. So for V coil here, we'll have to use the Pythagorean for this, and of course it's going to be VR squared plus VL squared, and then of course you can find V across the coil. But before I find any of these, I need the current. And in order to find the current, I need Z, or the total impedance. So total impedance equals to what? Equals to, let's write this one here. Total impedance equal to the square root of, let's say R, and by the way, since we have more than one R, so we can call it R total here, that is squared, and then I'll say XL minus XC, the whole thing squared. So what about the resistance here? I can perhaps find these here. So we'll say resistance total, because I have two resistance here. One of them is 12, the other one is 10, so we'll say 10 plus 12. That is basically 22 ohms here. That is for the resistance. What about XL here? XL is basically equal to omega L. Omega, that is 2 pi F times L, correct? 2 pi times frequency is 60 times the value for L, which is 15 times 10 to the power negative 3. I hope you can still see this. So find the value for XL. Let's assume that we found it, which is basically, I'll get it into a second here. And then for XC here equals to 1 over omega C. Once again, 1 over 2 pi F times the value for the capacitor here. So once again, 1 over 2 pi times 60 times the value for the capacitance, which is 200 microfarad, correct? That was it is. Okay, 200 micro, that is 10 to the power negative 6. So do the math, and of course you'll find each value. Once you do them, then you can plug the numbers into the equation, then you can find Z. Once you find Z, you can find the rest of the questions there. Okay, now that was basically, and then after that, all right, let's get into some numbers. I didn't want to spend time doing this, but I think I still don't need to do this. But here's, we have this is 22, that is squared. Let's do this properly since we began. All right, so 22, and then XL. XL is equal to what? Equals to 2 pi times 60, okay, multiplied by 15 times 10 to the power negative 3. The answer is going to be 5.65, you can say. Of course, we can, by rounding, we can say 5.7, yeah? Okay, so let's say this is 5.7. That is XL here. Okay, and then what about XC here? Okay, just let me double check with the numbers. I don't want to make any mistakes here. 60 times 15 times 10 to the power negative 3. That is again, okay, so that is 5.7 by rounding, we can say. That is in ohms, don't forget. What about this one here? That is the same thing. We'll say 1 over divided by, that is 2 pi times 60 times 200 microfarad, yeah, times 10 to the power negative 6. The answer for this one is going to be 13.3, we can say, by rounding. So this is going to be 13.3 by rounding. That is going to be in ohms here. So now we can plug in the numbers. So this is 5.7 minus 13, okay, minus 13.7, the whole thing squared, yeah? So you do the math, of course, you'll find the answer here. Okay, so instead of doing all this, how about if I just take a look at these numbers and I can tell you this, yeah? Okay, so basically XL was this. We can say 5.7, we say by rounding, and this is 13. So Z is about 23.3, we can say. Z is about 23.3 here. 23.3, this is in ohms, yeah? Okay, now I can, of course, I can find the current here. So let's say I equal to V effective over Z here. So V effective, that is the voltage of the source, which is 100 divided by 23.3. So what would be the current here? 100 divided by 23.3. The answer is 4.29. We can say 4.3 by rounding. That is amperes. If that is the current, then of course you can plug in these numbers into this, and of course you can find everything that you need to, and that's that simple here. Okay, so I'll write the numbers, you do the math, and of course you can plug in the numbers later. So we can say 4.3 times, let's just make this one a bit nicer, 4.3 times the resistance. By the way, we're talking about the pure resistance, okay? So pure resistance was 12. It was 12, yeah? So 4.3 times 12. You'll find the answer here. What about this one here? That is 4.3 times XC. XC we found over there, yeah? Which is about 5.7, we can say. So 5.7, you'll find the answer. That is going to be, these are all in volt, by the way, okay? Because we're talking about the potential difference across each one of these components. But there is something you need to be aware of, yeah? And that is, because for the coil here, we have two parts. We have the inductance, you can say, and of course self-inductance, and of course the resistance here. So I'll find the voltage across the resistance of the coil. The resistance of the coil was, that is for the current, the resistance was 10, yeah? So you do this one, of course, that is going to be 43. And for this one here, 4.3 times XL, we found it, yeah? Which was 13 point, what was it? I think I've made a mistake here. Okay, instead of this 5.7, it was for the XC, my bad, yeah? As a matter of fact, it was for XL here, so I'll have to write 5.7. 5.7, okay, this is, you can do this one here for XL, but XC was 13.3, so for this one, where did I erase this for? Okay, so VC, of course, is going to be 13.3. You do the math, of course, you'll find the answer. Now, once you find the answer or the voltage across each one of these, now put these values into this, you will find the voltage across the coil, and of course, is going to be this much voltage and whatever it is. Okay, so this is basically the first part of the question. Now, going to the second part, it says the frequency of the alternating current that allows the circuit to resonate. Okay, so how do you find the frequency of the circuit that allows the current to resonate? Now, I think this is simple again, yeah? So how do you find the frequency of the circuit, by the way? All right, so the next thing that you need to do is finding the frequency that this circuit is going to resonate with. Okay. Now, let me ask you something. We said in resonating circuit, basically XC is equal to XL, yeah? That's one of the ways we can do that. Okay, so I can say, without doing the, okay, how about if I just go ahead and undo this one here? We said we have one equation. We'll say f equal to what? F equal to 2 pi over the square root of L times C. Yeah? Do I have the value for L? Yes. Do I have the value for C as well? Yeah. So basically, you could just use this equation right away. You can find the frequency. If not, you can derive this equation from xc is equal to xl. Then, of course, you'll get to this one. You have the value for L. You have the value to C. Then you could just do the math, and of course, you will find the answer as simple as that. And that is going to be, the answer is going to be about 92 hertz. Okay, that would be for this one here. Okay, now take a look at this question here. That is also previously, or you can say pretty much, we've done a lot of questions regarding this. Yeah, you can say, it says find the impedance of the circuit if you have a coil with a resistance, you can say. And of course, the effective value for the current in the circuit, that is easy as well. And then, but one thing that perhaps I might want to do, this is this. It says find the capacitance of the capacitor that should be connected in series in order to obtain, yeah? In order to obtain what? In order to obtain resonance. And of course, this part, perhaps you can, perhaps it might be a little bit different than the previous one. You're going to equalize this to x is equal to xl. That is the only different, you can say, part here. And then, of course, this is 1 over omega c equal to, let's say, xl, since you can see that the value for xl is given, or you can say, basically, that is what it is. Yeah? It says an inductive coil of resistance of this much. Yeah? So we have xl. So you don't have to, for example, you just keep this one, and then you'll try to kind of like find the answer for this one, or the frequency for this one, then easily you can find the frequency of the circuit. And of course, it says the expression of the instantaneous value for the current during resonance. That is also another part which is very important, guys. Okay, so we do have, let's say, the V effective of the circuit, yeah? Let's get this back. Okay, now I want to take a look at this point here. It says the expression of the instantaneous value for the current here. Once again. Okay, so what do we want? We want the instantaneous current or value of current during resonance. So the instantaneous value for the current, of course, we have this equation. You can say I effective equal to I maximum, of course, sine omega t, yeah? Okay, so clearly you have the frequency of the circuit, so you can easily find omega t, that is 2 pi f, easily can be found. This t, that we'll write it the same. But what about I effective and I maximum here? Or how about I effective, guys? Remember, in order to find I effective, if this circuit is at resonance, then we will only consider this resistor part, you can say, or resistance part, without considering this one. Or you can say at resistance Z equal to R. If that is the case, then of course we will say I effective equals to V of the source divided by R in this case, yeah? Then if that is the case, let's say, we're trying to find I effective, by the way, yeah? So this is, we will say I instantaneous here, not I effective. So in this case, the value of the source or the effective, this is 200. The resistance of the resistor is 60. Where was it here? Actually, the inductive coil resistance, that is 80. So you divide the two. So 20 divided by 8, that is basically 2.5, we can say. So the current I effective is 2.5. But we don't want I effective for this equation. We want I maximum. So how do you convert or change I effective to maximum? Of course, we do have this equation. I maximum equal to I effective times the square root of 2. So 2.5 times the square root of 2. Of course, you can easily find, let's say, I maximum. Then, of course, you can plug in the equation into, let's say, into the main equation that we have. Okay. What else do we have? And these are a few other Wrya questions. Take a look at them. These are also something very important. It says, the circuit shown in the figure is a resonance circuit. So this circuit is in a state of resonance. If the effective potential difference of the source is this much and it is frequency this much, the equation of the instantaneous current in the circuit is this. I want you to be aware of one thing here, guys. Remember this, yeah? This is pretty much the same as the question that we've just, or the last part of the question that we have solved here. In a state of resonance, that means in a state of resonance, clearly, you can see that we can say Z is equal to, or total impedance, we can say total impedance, let's get this back, okay. total impedance here is equal to R, and of course we can say 22 ohms here. That is this. What else do we have? You have the voltage of the source, or V effective, that is 220 volt. You have this, you have R, you can find I effective. But don't forget, guys, these equations, what you see here, these are I maximum here, not I effective here. So once you find I effective, you'll have to find I maximum using I effective, okay, times the square root of 2, that is 1. Then, of course, once you find the answer, compared with these as well, yeah? And of course, they can simplify this. Remember, omega equals to 2 pi f. What is the frequency of the source? That is 60, yeah? So 2 pi times 60. 2 times 60, that is 120 pi, yeah? So these are, tells you 60 and 60, so these are not. So it is going to be either D or I in here, okay? Now we can do this one, of course. We can say that is 220 divided by 22, that is going to be 10, yeah? If you see 10, that is without the I maximum, so it is going to be incorrect. So it has to be 10 times the square root of 2 is more likely going to be option D here, okay? So you double check with the math, okay? Otherwise, this is how you can do that. Just remember to find I effective, okay? Once you find I effective, then of course, use or find I maximum, and you have the omega or frequency to find omega, then compare which one of these would be the correct answer to this. And this is something very similar to what we have said, and of course this one too, which I would recommend you to do them right after this. Okay, now we have something very interesting, but I'm afraid we ran out of the time for this session. So we're going to do this one in a different session. Till then, keep practicing. Make sure you go through this one more time, because this is very, very important, especially of course, there will be questions regarding resonance. So make sure you master all these concepts. And I really hope that you do. So till then, take care and keep practicing. Assalamu alaikum wa rahmatullah.